Okay, welcome everyone. So we have been working with diagonal matrices and matrices that are similar to a diagonal matrix. And so you may have some questions right now like, well, how do I know if a matrix A that I'm given is similar to a diagonal matrix? And how do I find this matrix P that's going to allow me to multiply A on the right by P, on the left by P inverse, and find this diagonal matrix? So we're going to answer some of those questions right now. So an n by n matrix A, again, is diagonalizable if we can find a matrix D which is diagonal and similar to it. So this is a special property. It is not possible to diagonalize every single matrix. So first of all, we can only do this to square matrices, and not all square matrices are diagonalizable. So the next theorem is going to answer these questions. That is, how do we determine whether a matrix is diagonalizable, and how do we find a matrix P so that when we conjugate A by matrix P, and when I say conjugate A by matrix P, what I mean is multiply by P on the right and P inverse on the left to identify what this similar diagonal matrix is. So this can be summarized in what is called the diagonalization theorem. And so what this theorem says is that an n by n square, in other words, matrix A, is diagonalizable if and only if A has n linearly independent eigenvectors. So that's our condition that we can check. Does A have n linearly independent eigenvectors? This is an if and only if. So if A does have n linearly independent eigenvectors, it is diagonalizable. We can find a similar matrix to it, which is diagonal. If A does not have n linearly independent eigenvectors, then it is not diagonalizable. And in addition, this theorem tells us if it is diagonalizable, how to construct a matrix P so that when I multiply P inverse times A times P, we can get this diagonal matrix D. And so the columns, we're going to set up this matrix P by finding eigenvectors of matrix A. And the columns of matrix P are going to be the n linearly independent eigenvectors. So we're going to find eigenvectors of matrix A, and then we're going to construct matrix P from those eigenvectors. And then the matrix D that we get back in the end is gonna be a diagonal matrix. The diagonal entries are going to be the eigenvalues of A corresponding to the ordering that we listed the eigenvectors in matrix P. So in other words, the first column in matrix P is some eigenvector, and that means that the first diagonal entry in matrix D is going to be the eigenvalue of the first column vector in P. The second diagonal entry in D is going to be the corresponding to the eigenvalue of the second column of matrix P. So let's take a look at an example on the next slide. Okay, so let's consider the following example. We have a 2 by 2 matrix A. The first column is 6, 2, and the second column is -1, 3. And we would like to identify whether this matrix is diagonalizable, and if so, let's diagonalize it. So you can verify that this matrix has two eigenvalues. So you can set up the characteristic equation and solve that characteristic equation. And one eigenvalue is 5, and a corresponding eigenvector for that eigenvalue is the column vector 1, 1. And so you can verify that if you take this matrix A and multiply it by the column vector 1, 1, we'll get a scalar multiple of that column vector back. We'll get the vector 5, 5. So this means that 5 is an eigenvalue with eigenvector 1, 1. And you can similarly verify that there is a second eigenvalue for matrix A, which is 4. And this eigenvalue 4 has an eigenvector, which is 1, 2. So we have two different eigenvalues. Each of them has a basis for its eigenspace, which is spanned by one vector. So you can see that these two eigenvectors are indeed linearly independent from each other. So since we have two linearly independent eigenvectors for this 2 by 2 matrix A, I know that A is diagonalizable. And in addition, I also know what the matrix P should look like. And so this matrix P is going to have two columns in it. And so you can see the first column is eigenvector 1, 1, and the second column is eigenvector 1, 2. And when I multiply the matrix A, 6, 2, minus 1, 3, times this matrix P, notice that because 1, 1 is an eigenvector, taking this matrix times this first column 1, 1 gives me 5, 5. And because 1, 2 was a second eigenvector, this matrix A times this second column of matrix P is going to give me 4 times this column, is going to give me 4, 8. So far, what we can see is that the product of A times P gives us this 2 by 2 matrix, 5, 5 in the first column, 4, 8 in the second column. And this matrix, 5, 5, 4, 8, we could also write as the product of P on the left times a diagonal matrix D on the right, where this diagonal matrix, the first entry 5 corresponds to the eigenvalue of the first column of matrix P, and the second entry on the diagonal of D corresponds to the eigenvalue of the second column of matrix P. So what we can see here is A times P is equal to P times D. And multiplying this relation on the left on both sides by P inverse gives us exactly this relation, that P inverse A times P gives us D, because that is going to give us the identity matrix. So this is one way to verify whether your matrix P does the trick, is to check to see whether AP is equal to PD, and that's going to be a little bit easier than checking the full condition, which I have below, which would require us to actually find the inverse of matrix P and then take the product of these three matrices. But you can verify that by multiplying P times D times P inverse, indeed we do get matrix A back. So just to clarify what was the point of this example, well, we had a 2 by 2 matrix A, and first we wanted to identify whether we could diagonalize it, and since we found two linearly independent eigenvectors, we can diagonalize it. And then we use those two vectors, those two eigenvectors, to identify the matrix P, which we need to express A in its similar diagonal form. And then we discussed how we can actually verify that our matrix P does the trick by checking to see if A times P is equal to P times D. So let's generalize this process on the next slide so that we can get a sense for why the diagonalization theorem is correct in general. Okay, so based on that 2 by 2 example, we now have a sense for how we can prove the diagonalization theorem in general. So what the diagonalization theorem states is that an n by n matrix A is going to be diagonalizable if it has n linearly independent eigenvalues. And in that case, the matrix P that we need to diagonalize A is going to consist of columns that correspond to each of the eigenvectors of matrix A. So let's assume we have a matrix A that has a collection of n linearly independent eigenvectors that we'll call V1, V2, up to Vn. And then let's construct this matrix P where the first column is going to be eigenvector V1, the second column is eigenvector V2, and then lastly, the nth column of matrix P is eigenvector Vn. And now let's take the product of A times P, where we're multiplying on the right by P. So that is going to look like A times this vector where each column is one of these eigenvectors. And that means we can calculate the product by taking A times eigenvector V1. The second column is going to be A times eigenvector V2 all the way out to the last column would be A times eigenvector Vn. And then we can use the fact that V1, V2, Vn, these are all eigenvectors corresponding to the eigenvalues lambda 1, lambda 2, all the way up to lambda n. So this product is going to simplify to lambda 1, V1, lambda 2, V2, all the way out to lambda n, Vn. And now this product is equivalent to taking the matrix P, which again is the matrix whose columns consist of these n linearly independent eigenvectors, times this diagonal matrix on the right, where the entries along the main diagonal are the eigenvalues lambda 1, lambda 2, up to lambda n, where these lambdas appear in the same order consistent with how the eigenvectors are forming this matrix P. So this tells us that A times P is equal to P times this diagonal matrix D. And this condition is exactly the same as verifying that P inverse A times P is equal to D. So this general proof that we just walked through is very much the analog of the 2x2 case that we worked through more specifically.